Okay, I've jumped ahead in time. I don't remember where I was. We did 9. I just did 9. I don't feel like doing. It's really late. It's 1:16 in the morning. I don't feel like doing 12. 15 is the same as 18, only easier. So I'm gonna work on 18 and get that posted for you guys. And probably I'll go back and do the other ones too. But for right now, I want to just make sure 18 happens. Um, and that's not the same as the one we did before, right? I'm pretty sure those are new numbers. Um, so we'll go ahead and go. Let's do it. As always, we're going to start by considering the domain and range. And we've talked a bunch about how the domain of a rational function is always going to be all real numbers, except for the zeros of the denominator. This denominator pretty obviously has a 0 at 2. If you let x be 2, you would have 6 minus 6 giving 0. So 2 is the value that needs to be excluded from our domain. Again, if it wasn't so obvious that x was 2, you can always grab the denominator and just set it equal to 0 and then do the math. You're going to add 6 and divide by 3. And there's your 2. So if ever these numbers were uglier, I mean, you can do it as an algebra problem off to the side, get your value, record it. Okay, we also know that when we're working with a fairly simple rational function, and when I say simple, I mean a linear over a linear, we know that our range is going to be all real numbers except for the y value of the horizontal asymptote, right? So what's that going to be? Well, this is another one of those ones where the numerator is degree 1 because it's linear, and the denominator is also degree 1 because it's linear. So we know that the rule for that is that the horizontal asymptote is going to be the two leading coefficients. It's going to be 4 divided by 3, or 4/3. So we know this function has its horizontal asymptote of 4/3. So that would be the one and only y value that we do not map onto. Again, if you were going to sketch this graph, then 2 being a 0 of the denominator implies a vertical asymptote at 2. And then the leading coefficients being 4/3 implies that at 4/3, or 1 1/3, we have our horizontal asymptote. And then you know you're going to be a hyperbola that fits into 2 of these diagonal quadrants, so to speak. But which quadrants? You don't really know until you test some points. And pretty much always you just test 0. Plugging in 0 is almost always going to be the easiest thing, because this would cancel, this would cancel. We would get 2 over -6 for -1/3. -1/3 is well below the horizontal asymptote. So we can see that we should be getting a branch that lives here, and then our other branch should live here. So there's a sketch. If you wanted a sketch, there's a sketch. Oh, I guess we did want a sketch because we're supposed to verify that we're 1-to-1. And we know we're 1-to-1 because, well, rational functions like this are going to be 1-to-1 when they're a hyperbola. All hyperbolas are going to be 1-to-1. I don't know what I'm saying. Why am I saying that? That's a dumb thing to say. Not all hyperbolas are 1-to-1. That was incredibly stupid for me to say. Because most hyperbolas are the ones where you've got these asymptotes kind of intersecting like this on a diagonal. If you don't have a vertical and a horizontal asymptote, then you are certainly going to get a hyperbola like this. And that is very obviously not 1-to-1. That super fails the horizontal line test. We get a point of intersection, fails everywhere. So forget that I ever said that all hyperbolas are horizontal. What I meant was all the graphs of rational functions whose numerators and denominators are both linear, giving us a very specialized hyperbola with vertical and horizontal asymptotes, well, they're going to be 1-to-1. But all these other guys are not. Anyway, we're 1 to 1, so let's go ahead and find our inverse. And we'll find our inverse by taking this function and inverting all the variables, right? So we're going to have y equals 4x plus 2 all over 3x minus 6. And when we flip the variables, we would have x equals 4y plus 2 over 3y minus 6. And the algebra here is a little weird and a little different, but I don't think it's hard. I still say that your first approach should be essentially just to multiply through by this denominator to make it cancel. But a cleaner way to think about that is that you're just cross multiplying. So when you cross multiply, you get x times this. And go ahead and distribute the x. So you get 3xy minus 6x. And that'll be equal to 1 times the 4y plus 2, so just 4y plus 2. Then the next big deal was to recognize that you've got a term here involving y, but you have another term over here involving y. And you want to get those y terms together. So I'd leave the 3xy alone, and I'd subtract 4y from both sides. But I want this term here that doesn't have y in it, I want that thing gone. So I'll add that to the other side. And that'll give me 6x plus 2. Okay, well now that my y terms are together, I want to turn that one y, I want to turn these two y's into just one y. So hopefully you're noticing that they are common. It's a common factor now. So you just factor it out and you get 3x minus 4. And so by factoring it out, the two separate y terms become just one y as a coefficient on the 3x minus 4. So in our attempt to isolate y, we've done it. We got y alone. And so now to isolate it, we just divide by the other thing. And we'll get y equals 6x plus 2 all over 3x minus 4. And I did say that instead of y, you should be embracing the whole inverse function notation. So you'll say f inverse of x. The other thing we should do is factor. Anything we can factor out, we're supposed to factor. So that includes just pulling out a factor of 2, just so you can say 3x plus 1 all over 3x minus 4. But there's our inverse function. If we've done it all correctly, then the domain of the inverse function should be the range of the original function, which is all reals except 4/3. And for that, well, look at our denominator. 4/3 is the 0 of the denominator. So that is our restriction on our domain. So I'm feeling good about it. Get rid of that. That's supposed to be a 4. And then our range should be the original function's domain, which is all reals except for 2. And then I do feel good about that because, not so obvious here, but up here, I can see that if I take my leading coefficients, then my horizontal asymptote would be at 6 over 3, which is 2. So 2 would be the one value that's not in our range. So that's feeling good. If you want it to feel even better, then I could take it to Desmos. And the function that we just had was, I'm going to just type it in like the green version rather than the factored version, but 6x plus 2, 3x minus 4. So there you go. These are kind of hard to visualize, but if I also graph the line y equals x, if we get the color coding going, this should be black and skinnier. And usually I've been having the inverse function as a blue function. Then you can probably tell, if you cock your head just right, that the original function in red, this branch, when reflected, does become this blue branch. this red reflects and does become that blue. And so, you know, a little weird looking, but those are reflected images over the line like they're supposed to be. So I'm feeling happy with my answer. Again, how could we test this? We could look at a couple order pairs if we wanted to, but I feel fine with it. It's good. Moving on. The last thing we have to do with 18 is verify that everything is the inverse by doing the composition, and that gets you know, tedious, we said, but let's copy this, go to a fresh page where we've got plenty of room, and let's grab our inverse function. Again, I think I'm going to work with this version. Don't give me this version as your answer, but it would be okay if you did the math with this version. Cut. Paste. But there's the two functions. Dividing line. You know. On the left, let's do f composed with f inverse. Which means we're cramming the green thing into the black thing, which means we get 4 times the entire green thing plus 2 all over 3 times the entire green thing minus 6. So it's going to be 6x plus 2 over 3x minus 4. Okay, how do we clean this up? First of all, this 4 is just a 4 over 1. This 3 is just a 3 over 1. So that 4 is going to multiply into the numerator, giving me 24x plus 8. Then as far as this 2, that 2 is over 1, but we need a common denominator. So this needs to get hit with a 3x minus 4 over a 3x minus 4. Now from here, we've got sort of our big main fraction bar, but our numerator is a fraction too. And now that we've generated that common denominator, we can see that this denominator, the denominator of the numerator, will just be 3x minus 4. And the numerator of the numerator will be the 6x plus 2 times 4, so 24x plus 8, and then the 2 distributes in, so we're adding on an extra 6x and taking away an extra 8. This is our numerator. This is sort of the cleanest way we could get there, I think. And I see my big dumb face is about to get in the way, so we'll move my big dumb face. Yeah. Okay. So what's happening downstairs? Well, in the denominator will be 3x minus 4 again. The numerator will distribute the 3 to get 18x plus 6. Then we have to do the same with the 6. It's a 6 over 1. We need a common denominator, so 3x minus 4 over 3x minus 4. Distribute the negative 6. And up top, we see that we're subtracting 18x. And we are adding 24. So that whole big gray thing, that's the complex fraction that results from cleaning up all this garbage. And this is not as bad as it looks, because we know that right away, when our denominators are the same, we can cancel them, so they're gone. We also know that in the numerator now, we've got 24x's and 6x's. That's going to give us 30x's. Then we've got an 8 with a negative 8, so those cancel. Downstairs, we've got 18x minus 18x, so those cancel. And we've got 6 plus 24, which is, well, it's 30. So guess what? 30 cancels 30. The only thing left is x, which is the exact result we wanted, right? Having the functions composed, boiling down to x, it's exactly what we wanted. So I'm going to scroll back up. We're going to do it all again, but this time in the other order. This time we're going to compose the inverse function with the original. So we'll take our inverse function as our outer shell. So we'll go 6 times x plus 2 all over 3 times x minus 4. And we're plugging in the original, so 4x plus 2. 3x minus 6. Okay, so we know that once we clean this up, we're going to have a big fraction. The numerator is a fraction, denominator is a fraction. The numerator will have a denominator that's just 3x minus 6. And so will the denominator. So those are really just going to cancel right out. So what's happening in the numerator? That's going to be the more important thing. Well, here the 6 distributes into the numerator. We get 24x plus 12. But then we're also adding on 2. 2 over 1 multiplied by 3x minus 6 over 3x minus 6. That's to generate that common denominator. So that means we're actually adding on 6x and taking away 12. And the same thing happens in the denominator. Distribute the 3, 12x plus 6. This is going to get multiplied by 3x minus 6 over 3x minus 6. And we're distributing a negative 4 in. So we'll be subtracting 12x. And we'll be adding on 24. And now it's just like before. We can definitely just cancel those denominators. Then 24 and 6x makes 30x. But the 12 and the 12 cancel. And then in the denominator, the 12x and the negative 12x cancel. But the 6 and the 24 make 30. So we see again that we can cancel the 30s to land on just plain old x. And so now we can say, you know, since both compositions equal x, we know that the function we found to be our inverse is definitely correct. It really is the right inverse. So let me shrink this. And then shrink this. And maybe this needs a little bit of a shrink. Then go back to whatever. Was it on 100% or something? Yeah, whatever. You guys can probably make that out well. I'll leave this slide up for a second. You guys can pause it, obviously, and leave it up forever. But this math is pretty important. Being able to compose these like we did, the algebra gets a little iffy, gets a little weird. But we did it twice. Hopefully you understood one of those explanations. And they're both really similar. But you will certainly be on the hook for knowing how to do that. So is that it? Did I cover everything well? Yeah, we talked about the domain and range. We talked about how they switch. We talked about the graph. We talked about everything. So that ought to do it. You guys, I hope, are feeling okay. So this definitely should be best fit. Yeah, that looks way better. Okay. I think that's it. I'll move myself over there. I think I'm done making videos for the night. It's very late. I'll try to get the rest up tomorrow so you guys can study for the quiz. And I hope you'll use these resources too when it comes time to study for your test. Anyway, good night. See ya tomorrow.